All right. And we are live, question mark? Have a little sip of tea while I wait for the latency. Ooh, it's a little hot. All right, it looks like Twitch is go, and it looks like YouTube is go. Hello, good morning, everybody. Or morning, evening, wherever it is where you are. Welcome to the reading group. We are starting a new paper today, and I promised last time that I would have a vote to pick the new paper, and the options were that paper where you get parse trees from the latent space of language models, which got the fewest votes, and then it was the sparse transformers for sequence generation paper, which actually going into it I thought would be the winner, because it's more image and also image and text, and I know people have been asking for more image stuff, but the winner was this paper, MultiTask Deep Neural Networks for Natural Language Understanding. Hello, Abnav, welcome. Sorry if I got that wrong. Yes. Okay. So I've been doing a little bit of digging into this paper. So it is out of Microsoft Research, MSR. If you hear me say MSR, I mean Microsoft Research. I'm in Seattle, which is kind of close to the, hello, Henry, kind of close to the Microsoft headquarters. So I know quite a few people at Microsoft Research, even though they've, a while ago, they sort of pared down their research teams, which was sad for me personally, because there were less people working on things I was interested in the area. But this is a paper out of that research division. It's not really a group. A group is more like people working on the same problem together. And I did a little bit of digging, by which I mean I looked it up on Semantics Collar. So if you're not familiar with Semantics Collar, it's just sort of basically it's a knowledge graph and way to explore scholarly publications, and it is really bad for some fields, but it's pretty good for computer science and NLP in particular. Because I just sort of wanted to see where this was in the literature. So one thing to note is that it has not been published in a scholarly venue. It's been put on archive, which means it hasn't been peer reviewed, that we know about, that it hasn't been published in a venue that requires peer review. Let me put it that way. So that's something to keep in mind. We've read other papers that weren't peer reviewed. The BERT paper wasn't. The GPT-2 paper wasn't. So be a little bit more on our, being skeptical, because we haven't had somebody do a pass before. Hello, everybody who's talking in chat. Asamala and Siwe. And it's building on the vein of work we've been looking at. So we read the BERT paper, we skimmed the GLUE paper. So GLUE is like a big suite of tests, and the idea is that instead of having your model do one task, you apply it across a bunch of tasks and see how generalizable it is. And this is specifically for natural language understanding. And we will go back and read the abstract in the paper because it's the same abstract. Sorry, I'm just a little gross today. I'm allergic to something, I think, and I don't know what it is. And I've been slowly trying to weed things out, so to speak. I think it might be something that's blooming now. I don't know. It's spring in Seattle right now. So some things that I noticed. So there is a video, and it looks like this is in Mandarin probably. So I'm not going to watch that, but if you all speak Mandarin, this might be a good resource for you. And then also they made their code available on GitHub, which is really nice. So this is... Oh, I need to go through and do that at some point. Anyway, so if you don't have to confirm your account recovery settings, you can check that out. And then it's got the figures. And the thing that I thought was super interesting was So these are the other papers that have cited this paper, and this paper hasn't been out super long. It was published this year. Well, made public this year. And there have been a couple papers, and one of them is by the same authors. And then there's another one about multitask networks for natural language understanding by anonymous, I guess. That's probably on arXiv as well. So there's two papers already that this paper has really influenced, and one of them is by the same authors, so it's, I don't think it counts as highly. And then looking at papers that were really important for this paper, BERT, which we read, and GLUE, which was referenced in BERT, which is this sort of benchmarking task paper. And then some things that I'm less familiar with, and it looks like these are by the same author as well, one of the same authors, so Xiaodong Liu, and actually looks like there's quite a bit of overlap. So it looks like stochastic answer networks are sort of a focus of this particular research group, so I imagine we'll learn more about that. And then textual entailment. I feel like I've read about this particular data set before. She says, I think that should be Japanese. Is that Japanese? Potentially Japanese. I don't see any characters that look uniquely Japanese to me, but perhaps you're right. Okay, so that's sort of the background of this paper. This is building on the BERT paper. It's building on the same task set as BERT. Henry says, Semantics Collar looks really cool. How did I manage to miss it? I don't know. I know about it because it's a research project from the Allen Institute, which is also in Seattle, and I attended a talk while I was in grad school about Semantics Collar and some of the work that they did. And it's really helpful for sort of positioning a paper in the literature, which sometimes NLP and computer science fields and machine learning in particular tend not to be the most meticulous about their literature reviews. And that's partially sort of a constraint of space, and partially I think it's a disciplinary norm. So it can be a nice way to get an idea of the sense of the paper. Okay, so let's learn about what the thing is now that we know sort of the tradition that it's in. In this paper, we present multitask deep neural networks, MTDNN, for learning representations across multiple natural language understanding tasks. So natural language understanding is sort of context knowledge and common sense reasoning and inference. So not just sort of the vector semantics thing where you know that cat and dog are sort of similar to each other in some sort of latent space, but that, higher level reasoning. Jesper says, whoa, I'm on time. Hello. Glad you made it. MTDNN does not only leverages large amounts of cross-task data, but also benefits from a regularization effect that leads to more general representations to help adapt to new tasks and domains. So they're using a lot of data across a lot of tasks, and this is leading to a model that is very generalizable and can move easily from task to task. Is the claim that they're making. Well, we'll see what the evidence is. Sorry. Trippy. MTDNN extends the model proposed by Liu et al. 2015, this particular researcher, by incorporating a pre-trained bidirectional transformer language model known as BERT. Okay, so it's building on previous work using the BERT architecture. MTDNN obtains new... Oh, am I going to sneeze? Okay, maybe not. Obtains new state-of-the-art results on 10 natural language understanding... Oh my gosh, sorry, this is super frustrating. On 10 natural language understanding tasks, including SNLI, which I think is one of the ones that was super stochastic. SNLI. I don't know. We'll learn more about it. SciTail. Oh, SciTail was one of their very influential citations. And 8 out of 9 GLUE tasks pushing the glue benchmark to 82.2%, 1.8% absolute improvement. We also demonstrate that using SNLI and SciTail datasets that the representations learned by MTDNN allow domain adaptation with substantially fewer in-domain labels than the pre-trained BERT representations. Excuse me for just a second. Sorry, I can't mute, it'll unsync the audio. Gross, nasty, ugh. Okay, that's better though. Sorry, guys. Our code and pre-trained models will be made publicly available, and they were made available. Okay, so the difference in performance between MTDNN and BERT is that MTDNN outperforms BERT, so it sets a new state of the art, and it's also more generalizable, and the representations allow domain adaptation with fewer in-domain labels. So it's generalizable and it doesn't require as much task-specific fine-tuning. The answer to life says, wait, I thought BERT wasn't really a language model. I would call it a language model. Yeah, I'd call BERT and GPT-2 both language models, but it's sort of like a language model plus. It's a language model that's intended to contain a lot of information. I guess all language models do that. So I would call BERT a language model, but like a fancy language model. Okay, so they're saying that they have a new type of model and it's better than BERT. Sorry. Introduction. Learning vector space representations of text, e.g. words and sentences, is fundamental to many natural language understanding tasks. Two popular approaches are MultiTask Learning and language model pre-training. In this paper, we strive to combine the strengths of both approaches by proposing a new multitask deep neural network. Interesting. Okay. So vector space representations, word embeddings, what's the other thing that they're called? Woof. Word vectors. Woof. Are ways of condensing usually a co-occurrence matrix. So things that tend to be used together are more like each other. And this has borne out pretty well in practice on the word level. Sentence embeddings are a little bit more controversial. And the one of the papers we didn't read has evidence that perhaps embeddings can capture syntactic informations and relationships between words. Oh, thank you, Nicotubba. But they don't, that's not explicitly their goal. So I think it's a little bit controversial to say that sentence embeddings are necessary for natural language understanding. I think if they got a reviewer who was not down with sentence embeddings, they'd get docked for that, or at least get a comment on it. Okay, so multitask learning is when you are training a single model to do a few things at the same time. I'm trying to come up with a good example. I don't know why I'm just like fuzzy in the brain this morning. And then language model pre-training are things like BERT, where you've got a really big language model, and then you can apply it to different things. In this paper, so they're going to combine both of them, presumably by training a language model on multiple tasks. Based on the title of the paper, that's what I'm expecting. Multitask learning, here we go, is inspired by human learning activities, where people often apply the knowledge learned from previous tasks to help learn a new task. In the pedagogy literature, this is called scaffolding. One of the things that this can be called is scaffolding. I'm not super deep in the pedagogy is like human learning. For example, it is easier for a person who knows how to ski to learn skating than one who does not. Similarly, it is useful for multiple related tasks to be learned jointly so that the knowledge learned in one task can benefit other tasks. There was a really good talk about this by, what's his last name? What's his first name? He's Dutch. Starts with an A, I think. At EMNLP, maybe in 2016. I definitely did a live tweet about it. I might go back and check it out. Excuse me. I thought you said Pentagon. Was really confused for a while. Oh, Pentagon. No, pedagogy. Pedagogy, maybe? Don't quote me on that. Streaming. Spelling is not my strong suit. Okay, so learning multiple things together. So if you can already do something similar to what you're trying to do, it'll be easier for you. And if you're doing things that are similar at the same time, then knowledge learned in one task can benefit the other. Recently, there is a growing interest in applying multitask learning to representation learning using deep neural networks for two reasons. First, supervised learning of deep neural networks requires large amounts of task-specific labeled data, which is not always available, true, especially in languages that aren't English. Multitask learning provides an effective way of leveraging supervised data from many related tasks. So it gives you more data to train your model, and as we know, especially for deep learning, more data is almost always better. Second, the use of multitask learning profits from a regularization effect via alleviating overfitting to a specific task, thus making the learned representations universal across tasks. Wow, that's a strong claim. So they're saying if you're training on one task, you're going to overfit your model to you. There's a probability that you're going to overfit a model to a specific task, especially if you have a lot of data. Which makes sense. So you get to the point where your model is basically memorizing your data set. And they're suggesting that if you use multitask learning, I don't know what I'm allergic to, but I'm going to find it. They're suggesting that if you use multitask learnings, your representations will be universal. They'll work on any task, which I think is an extremely strong claim that I do not see evidence here for. I would say maybe like more transferable. Because I wouldn't expect representations learned for like... I'm trying to think of two tasks where I don't think you'd get a lot of things. I don't think representations learned for like summarization would necessarily be helpful for a sentiment analysis task right off the bat. But one for like emotion categorization and one for sentiment analysis probably would be. Jesper says, would have been a good choice to cite one model to learn them all by Kaiser and then an archive link. Let's take a look at that. So this is a paper I'm not familiar with. Kaiser et al. 2017. I don't know if this has been published. Actually, one sec. I got Semantics Collar open. Let's take a peek. That's right. And it looks like it has been cited quite a bit. And 67 citations, so highly cited in their sort of distribution. And the idea is that you want a single model that works across multiple domains. Okay, and so this is a trained model. This isn't a very transferable architecture. Oh yeah, I remember this paper. I remember when it came out. I remember hearing about it. Ryan says, I'm more interpreting it as universal to the tasks it was trained on, not universal to all tasks. Universal across tasks. I guess that could be what they mean, but I interpret this as saying that it will work equally well on any language problem. Learn in 15 Minutes says, the Pedagogical Pentagon, a conceptual framework for artificial pedagogy. If somebody wants to write that paper, that would be fun. I would read that. Okay, so that's multitask learning. So I guess an example of a human doing multitask learning would be maybe a child learning how to cook, learning how to chop, and learning how to stir both rely on fine motor skills in the hands and like visual feedback. So if you're learning to do them together, the fine motor skills that you learn for chopping will help you with stirring. That's my great example. One sec. Sorry, I wish I could mute the mic, but that will, there's a couple of videos that are recordings where the audio and the visual are unsynced, and it's because I muted the mic and it's awful. All right, so that is multitask learning. Language model pre-training. So we've read a lot of papers in this particular genre, and so you can go and read those if you're interested. In contrast to multitask learning, language model pre-training has shown to be effective for learning universal language representations by leveraging large amounts of unlabeled data. A recent survey is included in Gao et al. The old citing a survey paper so you don't have to rewrite it trick. It's a good trick. I would recommend it, assuming that you have read and understand the survey paper. Some of the most prominent examples are Elmo, which we didn't read, but we did read Peter's second paper, GPT, we read the GPT-2 paper, and BERT, which we read. These are neural network language models trained on text data using unsupervised objectives, which is almost always true for language models. Inri says, so is one model to learn them all related? Should they have cited it? I think it's conceptually related. I would say that they should have cited it if they were, if they read it, but it looks like this is more based on the citations. It looks like it's a little bit more of a, it looks like it's a little bit more of a ML paper than NLP paper, although it was cited at Interspeech, which is sort of a marginally NLPE conference. So they possibly have just not run across it because it's in a slightly different domain as the one that they're working in. Disciplinarity. Ask me about it sometime. So I'd say, yes, if they'd read it and been influenced it, they should absolutely have cited it. Sometimes you just don't know that a paper exists. And being told about those papers and then having the chance to go read them and place your work in a better conceptual framework is one of the benefits of peer review. And this paper has, as far as we know, not been peer reviewed. So, little grain of salt there. Okay, where were we reading? So we were talking about the big neural networks language models, which people have been very excited about. And have had some exciting results. But like I said on Twitter, they are one tool. There are many tools. We don't necessarily want to replace all of the NLP work we've done over the past, 50 years with big neural network language models. For example, BERT is based on a multi-layer bidirectional transformer and is trained on plain text for masked word prediction and next sentence prediction tasks. And we've read about this. You can go watch those videos if you're interested. To apply a pre-trained model to specific NLU tasks, we often need to fine-tune for each task the model with additional task-specific layers using task-specific training data. For example, Devlin et al. Show that BERT can be fine-tuned this way to create state-of-the-art models for a range of NLU tasks, such as question answering and natural language inference. I'm trying to remember if they did have state-of-the-art on natural language inference. I know that the GPT-2 model really struggled on some of the more semantically, sort of like the more semantics, but like phrase level semantics things. We argue that multitask learning and language model pre-training are complementary technologies and can be combined to improve the learning of text representations to boost the performance of various NLU tasks. So their contribution is that they're using these big language models, or I'm guessing they're training their own, and they're also doing multitask learning. So instead of having a language model that's being trained in an unsupervised way, like fill in the blank, like BERT is, it'll be trained in a multitask way, I guess. I don't know how you would train a language model for a specific task without just having like domain-specific text. So the little language model history, the sort of traditional way of building a language model, or at least like the one that I learned when I was in grad school, is using, oh my gosh. Oh, wow. I see the diagram in my head. Markov chain. Wowzers, wowzers, wowzers. So you sort of have, given your corpus, you have a word, and you have the transitional probabilities to other words in the corpus. For most of them, it's going to be 0 because it's very sparse, and then you can sort of go to the next word, and then you have the transitional probabilities from that word to the other words in the corpus, etc. So you end up, a language model in that sense is sort of like a web that tells you how likely you are to go from different words. Wow, that took a minute to get out of the oatmeal this morning. Maybe I should have had a second coffee. I've got some tea this morning. All right. To this end, we extend the MTDNN model originally proposed in Liu et al. By incorporating BERT as its shared text encoding layers. Okay, so they use their model, and then they sort of are using that as the fine-tuning to replace the top. Okay, so they're taking BERT, they're putting BERT on the bottom in the way that you would use just sort of your general vector representation, so the way you might use glove in your model. So taking the BERT representations, and then they're doing MultiTask training on top of the BERT representations, and then it's better. So it's not quite ensembling as much as it is, oh, it might be. So I don't know if this is trained BERT or if they're training a BERT model. So I don't know if they're using a pre-trained model or they're training a model themselves. So basically they're taking their model and the BERT model and just like sticking them together. And he says, transfer learning? Yeah, I don't know what the difference is between transfer learning and multitask learning. I guess multitask learning, both tasks are updating the model, and then in transfer learning, it's one task updating the model, and then you stop and you move to a second task, and then the second task is updating the model? Does that sound right? Yeah. Josh says, transfer learning, you only fine-tune the final layers. But that's still what BERT is doing. So I guess BERT, as it's applied to specific problems, is transfer learning. Okay, and they have a figure. Multitask learning, Arsad says, multitask learning may be running parallel models. And Jer says, yes, I understand it that way. Hi. Jesper says, isn't transfer learning, so YouTube must be like about 5 seconds behind Twitch. Isn't transfer learning using a pre-trained model on one task and using it on another task? That sounds right to me. And then Jade says, is multitask learning the same as meta learning? I don't know. Is multitask learning the same as meta learning? Meta learning, so that's learning about learning, right? So that's more like finding a generalizable, is meta learning about architectures, or is it about weights within a given architecture though? And NJ says, if they're using a pre-trained model, is there any evidence that their improvements aren't just from more data? I don't know. I guess we'll find out. It's very possible that they just have they've gotten more information from the fact that they were exposed to more data. And Inri says, meta learning is completely different. Okay, that's helpful. I will look that up in my own time. Okay, so that's sort of their general idea, so using BERT on another task would be transfer learning, but the multitask learning is that they're trying to learn the same tasks, 2 different tasks using the same model. Ryan says, I've never toyed with multitask training. Do they cycle through the various tasks while learning, or train one and then move to the next? Never seen that spelled out. I also don't know. Hopefully we will get to that later on in this paper. And Inri says, meta-learning is quite abstract, e.g. a student endlessly tweaking his model optimization procedure could be considered meta-learning. Oh, it sounds almost philosophical. Okay. Oh, Jasper says, I understand why there are comments you respond to I don't see on YouTube. Yeah, I do YouTube and Twitch because I know people prefer different platforms. And I try and keep up with both of them. Okay. As shown in figure 1, and hopefully we will learn about whether multitask learning is sort of 1, 2, 1, 2, or 1, 1, 1, 2, 2, 2. Shared task. As shown in figure 1, the lower layers, i.e. the text encoding layers, are shared across all tasks, while the top layers are task-specific, combining different types of NLU tasks, such as single-sentence classification, pairwise text classification, text similarity, and relevance ranking. Similar to the BERT model, MTDNN is trained in 2 stages, pre-training and fine-tuning. Unlike BERT, MTDNN uses MTL, MultiTask Learning, in the fine-tuning stage with multiple task-specific layers in its model architecture. Trained in 2 stages. We got our pre-training, we got our fine-tuning, same as BERT. But the difference is that in the fine-tuning stage, we're doing task-specific layers in its model architecture. So instead of having BERT and then we have the fine-tuning for NLI and the fine-tuning for, I forget what all the BERT tasks. So instead of having a different layer for each of the glue tasks, we have the same model that we're using for each of the tasks, and then each of the layers is task-specific. That's what I'm picking up. Elbasari says multitask learning is used to share weights and applied on multitasks. Okay, so that is what my understanding is here. So I guess their argument is that in the original BERT paper, you had BERT and then you do different fine tunings, and their main contribution is that you have BERT and then you have their model, and it will do. Sorry, I'm not in the middle. You got BERT, you got their model, and then it'll do each of the tasks that it's been trained on without additional fine tuning. That's what I'm getting. Diggle Boy says, in multitask learning, you're using a DNN to do multiple tasks simultaneously in the hopes that each simultaneous task will help the other to produce a mutually beneficial outcome to the DNN. What I got from Ryan's question was, so you're doing multiple tasks at the same time. How do you calculate the error on that? So if the output of my model is, let's say, both NLI and I guess text similarity, because I'm just seeing it there, and one is wrong and the other's right, do I need to am I doing one output at a time and then back propagating through, or am I doing both outputs and then there's some sort of weighted function that I use for back prop? I got that was what Ryan's question was, which I also don't really know. We might, or you might, I don't know that we'll have time, go back and read the original MTDNN paper, and it might spell this out a little bit more overtly. Not overtly, explicitly. Inri says, multitask learning isn't NLP specific. It's a hot topic in deep reinforcement learning, for example. Oh, that makes sense. It seems like a sort of a general concept. And Jer says, the second one for all I have read. So where you're sort of doing one and then the other, and one and then the other. Okay, interesting. But maybe they'll talk more about it. So figure 1, lower layers, top layers are task specific. Let's go look at figure 1. Here we are. So this is their architecture. And I'm just going to read the text and then zoom in. Architecture of the MTDNN model for representation learning. The lower layers are shared across all tasks, while the top layers are task specific. The input X is first represented as a sequence of embedding vectors, one for each word in L sub 1. Then the transformer encoder captures the contextual information for each word and generates a shared contextual embedding vectors in L2 in here. Finally, for each task, additional task-specific layers generate task-specific representations, followed by operations necessary for classification, similarity scoring, or relevance ranking. Okay, so I was thinking that the architecture would be like all of, so the shared layers, and this is the lexicon, this is the transformer, so this is all BERT. And then I was thinking that there would be a single shared layer that was task specific, but it looks like there is sort of a different model for each of the tasks. So instead of having a whole model, it's one model with a shared bottom part that splits. So it's a single model, but I'm guessing you're saying what task you care about to apply it. Jared says, I was confused. The second one was combined loss function using some weight for one of the two, not to overwhelm the other losses. Oh, I see. So during training, we have an input, a sentence or a pair of sentences. It goes through, we get an output for each of these. We use some sort of weighting of the loss function, and then we prop back down, and then go up, and et cetera, et cetera. Except for the pre-trained ones, which don't change. Okay, I see. So the difference is that this is a single model and we're updating all of the weights in parallel across all of the tasks. That makes sense. Jesper says, is the model flowing upwards? So yes, this would be your input, this would be your output, and then when you're trading... Oh my gosh, I just want to sneeze. And then when you're training, backpropagation would flow back down and update the weights. Okay, I'm picking up what they're putting down. I should have looked at the picture first. This is making sense. Inri says, I guess they mask out the gradients for other tasks during backpropagation. My guess would be that they're doing them all at the same time. So Jared was saying that there's some sort of weighting. Ryan says, the problem with the weighted sums is you have different data for different tasks. The WNLI task doesn't also have a POS tag, potentially. Oh, interesting. So you might have data that's only annotated for one of your supervised tasks at a time. So maybe each of these switch off depending on, or maybe that's what the context embedding is, which of these. No, this is at the token level. Let's keep reading. If we sort of keep speculating, eventually I think we'll just confuse ourselves. All right. So we looked at the figure, and I think that makes sense. I'm just confused about, I guess I'm confused about how to use it, how it works. All right. MTDNN obtains new state-of-the-art results on 8 out of 9 NLU tasks. Yeah, you probably wouldn't be rewriting a paper if you hadn't gotten state-of-the-art on something. Using the General Language Understanding Evaluation benchmark, Wong 2018, which we talked about when we read the BERT paper. Pushing the benchmark score up, it's better than BERT, blah, blah, blah. We further extend the superiority of MTDNN to the SNLI and SciTail tasks. So these are additional natural language understanding tasks. The representations learned by MTDNN allow domain adaptation with substantially fewer in-domain labels than the pre-trained BERT representations. Sorry. Okay, so they're saying that they don't need... So the language model is trained on is unsupervised. You don't have labels, and then the task-specific training is supervised, and they're saying that their model needs fewer supervised tokens during training. Okay. For example, our adapted models achieve accuracy of 91.1% and 94.4%, outperforming previous, even with only 0.1% or 1% of the original data, the performance of NTDNN on both SNLI and SciTail datasets is fairly good and much better than many existing models. Interesting. So even with a very, very small sample of the training data, you still get fairly good performance. So that's definitely something that I'm interested in as a practitioner, especially if I have to annotate my own data. I would prefer to annotate less data or pay for less data to be annotated. So that's a potential benefit of this model. All of these clearly demonstrate MTDNN's exceptional generalization capability via multitask learning. So my one worry with this is so that you need much less data for each specific task, but do you need less data overall? Is the benefit not that you need less total data, but that your data can be more diverse? Because that seems like it might not be as good of a deal as it seems at first blush. And then talking about training, my intuition would be train on each task individually or in the confusion style loop and get better generalizable embedding vector. Interesting. Then you can reuse the same labels on different tasks. I guess the problem somebody brought up is that you don't necessarily need the same label output. We shall see. Hopefully they will talk about their training procedure a little bit more. The only glue task where MTDNN does not create new state-of-the-art is natural language inference, the old Winograd corpus. People really hate this one. But as noted on the glue webpage, there are issues with the datasets, and none of the submitted systems have ever outperformed the majority voting baseline, whose accuracy is 65.1. And I believe we looked at this previously, and there were some... nope, not helpful. Can I... Oh, I've lost my place. I got weird results. The train dev split for WNLI is correct, but turns out to be somewhat adversarial. When two examples contain the same sentence, that usually means they'll have opposite labels. The train and dev splits may share sentences, so if a model has overfit the training set, it may get worse than chance accuracy on WNLI on the dev set. Additionally, the test set has different label distribution in the train and dev set. Okay, interesting. So it looks like it's a little bit tricky for distribution of labels reason. All right. Oh no, I'm zoomed so far out. All right. Interesting. So the thing that's most interesting from here, I mean, I'm gonna be honest, I read enough machine learning papers that blah blah blah, state of the art, we improved X percentage points, is kind of boring. I'm kind of over it. But the use of less data is potentially interesting. All right, tasks. So hopefully now we'll get in answers about how this actually works. The MTDNN model combines 4 task types of NLU tasks: single sentence classification, pairwise text classification, text similarity scoring, and relevance ranking. Wait. Oh, I see. So it's split by the specific type of input the task takes and the specific type of output you need, not by task. So it's sort of split by task type instead of task itself. Okay, that makes sense. Because otherwise, if you were looking at single sentence classification, like, is this, I don't know, like abuse detection, and you got out the similarity between two sentences when you gave it one sentence, I think that would not be super helpful. So they have it, the multitask works, but each task that has a specific type of output has a different layer for it. Okay, so it's not actually task specific, it's task type specific based on the input and output. That makes sense to me. Where were we? Blah, blah, blah. For concreteness, we described them using the NLU tasks defined in the GLUE benchmark as examples. Single sentence classification. Given a sentence, in this study, a sentence can be an arbitrary span of contiguous text or word sequence rather than a linguistically possible sentence. What a sentence is like the thing that syntax is the field that studies. Ooh, that was, speaking of syntax. So that's, I would not have said sentence here. I would have said text span. This is another thing that folks with a lot of parsing background are just gonna be like, you can't say that. That's inaccurate. Okay, for example, the COLA task is to predict whether an English sentence is grammatically plausible. The SST2 task is to determine whether the sentiment of a sentence extracted from movie reviews is positive or negative. And I'm assuming when they say grammatically plausible here, they don't mean like, did you split the infinitive? Because that's something that you would see in natural language. I'm assuming they mean things like, well, actually, let's see. COLA, linguistic task, sentence, NLP. Let's see some example sentences. So an example of a grammatically implausible sentence is, books were sent to each other by the students. So the intended meaning here is that the students sent each other books, but that's not what the sentence means, I'm guessing. In which way is Sandy very anxious to see if the students will be able to solve the homework problem? So that is a that's an island violation. I'm pretty sure that's an island violation. Anyway, these are specific weird linguistic phenomena that violate syntactic principles, and I don't want to get too deep into syntax. But it's not like a grammar checker. It's a human would not say this checker. Okay, text similarity. This is a regression task. Given a pair of sentences, the model predicts a real value score indicating the semantic similarity of the two sentences. STSB is the only example of the task in Glue. I think you could also use this for like authorship identification. So given two text samples, how likely is it that they're written by the same author? Pairwise text classification. Given a pair of sentences, the model determines the relationship of the two sentences based on a set of predefined labels. Woo. For example, both RTE and MNLI are language inference tasks where the goal is to predict whether a sentence is entailment, contradiction, or neutral. And these are human labeled. So an example of entailment would be Rachel is sneezing, entails. Rachel bought tissues because she is sneezing, entails Rachel is sneezing. Rachel bought tissues because she is sneezing contradicts Rachel is not sneezing. And Rachel bought tissues because she is sneezing is neutral with regard to Rachel has allergies, because allergies may or may not cause me to sneeze. So there's sort of like semantic relationship potentially, but there's no semantic entailment. Some examples. QQP and MRPC are paragraph data sets that can consist of sentence pairs. The task is to predict whether the sentences in the pair are semantically equivalent. Okay, so I guess this is, yes, semantically equivalent, not semantically equivalent. Relevance ranking. Given a query and a list of candidate answers, the model ranks all the candidates in the order of relevance to the query. Okay, so this is like a search result sort of thing. So QNLI is a version of the Stanford question answering dataset. The task involves assessing whether a sample sentence contains the correct answer to a given query. Although QNLI is defined as a binary classification task in Glue, in this study we formulated it as a pairwise ranking task, where the model is expected to rank the candidate that contains the correct answer higher than the candidate that does not. We will show that this formulation leads to a significant improvement in accuracy over binary classification. Okay, I was like, why did they do this? And apparently it works better. And I don't have a strong sense without reading about why they did it, why that might be. So there's apparently there's a new version of Glue called Super Glue that just came out. This is from Ryan. They just have the manuscript. They don't have the benchmarking website set up yet. So that's something to check out. Okay, so these are the 4 types of task, and each task is slotted into one of these. All right, the proposed MT-DNN model, and hopefully we can get through this in 10 minutes. I am a little bit skeptical given the speed at which we tend to read the modeling sections. The architecture is shown in Figure 1. The lower layers are shared across all tasks, while the top layers represent task-specific inputs. The input X, which is a word sequence, either a sentence or a pair of sentences packed together, is first represented as a sequence of embedding vectors, one for each word in L1. Okay, so we take our sentence, we turn it into embeddings at the token level. Then the transformer encoder captures the contextual information for each word given self-attention, just like in BERT. And generates a sequence of contextual embeddings in L2. This is the shared semantic representation that is trained by our MultiTask objects. In what follows, we elaborate on the model in detail. So we start just each token individually, and then we do the attention, and then we have context vectors. So the what should I call it? The dimensions don't change, is what I'm getting from here, but the weights are updated. So words independent from each other, words in context. That's what I'm getting. Lexicon Encoder L1, this one. The input X, X sub 1 through X sub M, is a sequence of tokens of length M. Following Devlin et al., the first token is always the CLS token. And I believe that this was sort of the label for the specific task, if I'm remembering correctly. If X is packed by sentence pair, we separate these 2 sentences with the special token. So our input is label for the task or the pair, whatever it is that we're doing, embedding for each word. If there are 2 sentences, we have a sep token in the middle of the 2 sentences, and then embedding for each of the words of the second sentence, if there is one. The Lexicon Encoder maps X into a sequence of input embedding vectors, one for each token, constructed by summing the corresponding word, segment, and positional embeddings. The Lexicon Encoder maps X into a sequence of input, one for each token, summing word, segment, and positional encodings. Word, position, and segment. Word, position, and segment. Oh, that's right. I remember this. The position is the thing where they had like the weird function so that you had like each word had an index, but it was like a function of some sort of, I remember like polynomial something or other. And then segment is first sentence, second sentence. Okay, I remember this. It's all coming back. So we have the word, which is the embedding that we had, and then the position, which is sort of let's just say it's 0, 1, 2, 3, 4, 5 for each word in the span, and then the segment is whether it's in the first sentence or the second sentence. If there are multiple sentences, and if there's just one sentence, they're all in the first sentence, I believe, is the what those were. Okay, transformer encoder. We use a multi-layer bidirectional transformer encoder. So this is from the original transformer paper. Kumar says, do they create 3 embeddings for token and combine them all? I believe so. They mentioned that they summed them. So I think they take the embedding and then flip. They didn't say specifically what they did, but their code is also available, so we can check that out. Jer says, can you remind me if position is the topic we saw in attention is all you need? Yes, I think, let's see. Position, embedding, BERT. Nope, not embedding, encoding. Let's see. Position, just like in the previous step. I'm looking for a specific figure. The positional representation, blah, 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 blah. Positional embedding matrix will be as followed. Yeah, that's right. Yeah, this is the one where each position gets a unique item, and they use the weird sinusoidal encoding. Okay. Transformer encoder. We already read that. Okay. We used a multi-layer bidirectional transformer encoder, Viswani et al. So just half of it. They don't use the encoder and the decoder. They're only using the encoder, which makes sense because they're not doing sequence to sequence. They're doing sequence to label. To map the input representation vector into a sequence of contextual embedding vectors. That one. Big C is in the set of real numbers by D times M. So it's D is the length of something, and M is the length of the sequence of input tokens. So D must be just the dimensions that you've set. Jesper says weird sinusoidal encoding. Yeah, we talked about it in the BERT video if you want to go back and see it. But basically, instead of having 0, 1, 2, 3, 4, it's like it's generated based on the length of the sequence based on this sinusoidal function. I don't know that it actually does much. Unlike the BERT model that learns the representation via pre-training and adapts it to each individual task via fine-tuning, MTDNN learns the representation using MultiTasks Objectives. Okay, so these are the token encoding we read in from elsewhere, the attention part, the key value pairs. We are actually training via the tasks that we're doing. So yes, we are training a BERT-like model. Single sentence classification output. Okay, and so this is the way that they're doing each of the specific scores. Suppose that X is the contextual embedding L2 of the token CLS. So that's the label token that we use in the input that we just add a priori, which can be viewed as the semantic representation of input sentence X. AJ says the sign encoding is use of the model can handle positions it hasn't seen before during training. True, but the set of real numbers is infinite, and you can keep adding them. I'm sure it's very fancy math, but I haven't seen strong evidence that it changes model performance much. If any of you have a paper that does, I would be interested to see it. Blah, 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 blah. Take SS2 task as an example. The probability that X is labeled as a class, i.e. as class C, i.e. the sentiment, is predicted by logistic regression with softmax, where WSST is the task-specific parameter matrix. Okay, so we're taking the... Oh, I see. So we are only looking at the token CLS, which is our label token in the output, and then we're using our task-specific parameter matrix, and so task-specific here is for single sentence classification, and then so it's for all of the single sentence classification tasks, and then the probability that we have a specific label we get by doing softmax across this all of our task-specific parameter matrix given our contextual embedding of CLS. So we're looking just at the first token, we're applying our weights, and then we're taking softmax over that and saying like, okay, that's the one. Woo! Ow. That makes sense. Okay. Text similarity output. So that's for single sentence classification output. So text similarity, oh, one sec, let me open YouTube on my phone and do something real quick. I'll be right back. Actually, it is almost 10. Okay, so we will pick up next Wednesday on the text similarity output. So I think this is making more sense to me. I'm glad that we read down to here. We probably should have kept reading instead of just like hypothesizing about what it could be. I'm picking up their overall architecture. I'm interested to read more about it. Apparently the pairwise text classification is much more complex than the rest of them, so I'll do a little math warm-up. And I will see you guys next Wednesday. I won't be live streaming on Friday because I'm going to be at PyCon in Cleveland, and if you're there, you should come say hi. But if I have time, no promises, I'll try to record a video of a talk I gave a while ago and upload that on Friday. All right, so I'm going to call it now. I've got another meeting that I have to go to like right now. Thanks for joining, guys, and I will see you on next Wednesday for sure. Or PyCon if you're there. Bye.